Hello and welcome to XC Psychology. Today we're going to try to answer the question, is there table salt floating around in our blood? If you remember from our last episode, how do atoms become ions? We learned about ionic bond. That is when sodium says, hey, I don't want this electron, and chloride says, I'm going to happily take it. And they form something called a sodium chloride, and this is called an ionic compound. We also learned about covalent bond, which is hydrogen and oxygen shares their electron. So two hydrogen, one oxygen. And this forms a molecule called water. And this is called covalent bond. And the result is covalent molecule. So do we or do we not have table salt in our blood? The answer is yes and no. Yes, we do have sodium ions floating around and chloride ions floating around in our blood. And if you happen to taste our blood, if you had a paper cut, it tastes a little bit salty. But no, it is not in the table salt form, not in the crystal salt form. And let's follow this person's journey to understand it better. So imagine you have put some salt on the tip of your tongue. What would happen next is, well, we have saliva, right? The salt would dissolve and you wouldn't see the white crystal salt anymore. It would just be water. Now, let's have another look at water. Well, yes, we formed water with our hydrogen here, our oxygen here, our hydrogen again here, and they share two of the electrons, right? But it is not a very, static or stagnant form. It kind of constantly have the push and pull and trying to hold on to the electrons. And so in this tug of war, imagine oxygen has 8 protons. Proton is positive. Imagine oxygen is here. And hydrogen only has 1 protons. And so imagine who will win this type of war. The answer is very obvious, right? But it doesn't mean that, oxygen is just going to take away the electron from hydrogen. They're still sharing, but it's just like oxygen has a little bit more pull. So we can say that here oxygen is partially positive, and we use this delta notation to signal it. So if you remember delta as a triangle, that is also fine. And in this context, hydrogen is partially negative. So how does this matter? Why does this matter that oxygen is partially positive charged and hydrogen is partially negative charged? So when your saliva meets table salt, saliva is mostly water, and water molecule kind of said, hey, love you both, sodium chloride. You want to be friends? And they are actually have their own mind. Oxygen wants to be friends with one of them. Hydrogen wants to be friend with the other. And so what happened is that, let's look at sodium first. So sodium is very positively charged. And remember what we learned in the previous episode is that the opposite attract. So hydrogen being partially negative charged would be very attracted to sodium here. And oxygen being partially positive charged would be very attracted to chloride here. So they're still in the same form, they're still, H2O, but they're just, attract to different different ions. And so what will happen is they are both surrounded by water molecules, both sodium ion and chloride ion. And that is essentially what breaks them down is that, hey, I want to be friends with you. I want to be friends with you. I want to be friends with you. And so sodium is happily, befriended with more friends, and chloride has done the same. And so when you see, actually we don't see that, but when they enter into our body, especially in our cells, both sodium and chloride ions are surrounded by water. Now let's look at the journey of that salt landed on our tongue. So we have our taste bud. We have many taste buds in our tongue, and the taste for it is inside the taste bud. What will happen is the dissolved food molecules. So now we have dissolved table salt, sodium chloride. And once they're dissolved in the saliva, and they travel down to taste for, and remember now we have sodium and chloride ions. And we have something in our taste for called epithelial sodium channel. For the moment, we can understand that as a special channel for sodium. As long as it is sodium, the door will be open for it. And remember, sodium is very positive, right? Once it travels through inside the membrane, it will increase the positive charges inside the cell and fire an action potential. And action potential as sensory neuron to travel into our brain, that the part of the brain that is in charge of taste. And then our brain will say, that is salty. But bear in mind that the saltiness we taste is mainly from sodium ions, and chloride ions is almost tasteless. So why our blood needs salt, or specifically sodium ions? The first one is the blood pressure. The sodium acts like a sponge. Where the sodium goes, the water follows. And your kidneys will carefully regulate sodium levels to control your blood volume and ultimately your blood pressure. The second one is nerve signaling. Every time you move a muscle, pure sensation, or think of a thought, your nervous system relies on the movement of sodium ions. Again, if you watch the module 1, this is very easy to understand. Across the cell membrane to generate electrical signals called action potentials. The next one, fluid balance. Salt ions help maintain the right balance of water inside and outside your cells, and preventing blood cells from swelling and bursting or shrinking or swirling. And how much salt is there? For the normal range, a healthy adult has a blood sodium concentration of approximately 135 to 145 milliequivalent per liter. And for the normal saline, hospital commonly use 0.9% sodium chloride, known as normal saline. And this solution has a similar osmotic pressure to blood. So it doesn't cause cells to rapidly gain or lose water. It is basically designed for humans, this concentration. Why it matters: if an IV solution were to dilute by too few sodium chloride, or the cell would swell and burst. And if it's too concentrated, we have much more, the cells would shrink and shrivel. So normal saline helps keep our cells in balance. Key takeaways: table salt doesn't float around in our blood. Instead, millions of hydrated sodium and chloride ions are constantly empowering the chemistry that keeps us alive. Coming up next, why do molecules move without being pushed? If nobody's pushing molecules around, why do they never stop moving?